Hello, in today's video we're going to continue our discussion on sequences by discussing section 8.3, specifically geometric sequences. In previous videos we had talked about arithmetic sequences, which are sequences that have a common difference between terms. So for example, arithmetic might be a sequence that starts at the number 5 and then increases to 9, giving us a common difference of 4. So my next term would be 13, and then 17, and then 21, and so on. So that would be an example of an arithmetic sequence. That common difference here is a positive 4. Well, geometric has a similar pattern, except that instead of adding, we are going to be multiplying. So geometric has what we call a common ratio. So if I start at the number 5 and multiply by 4, I would get 20. So here my common ratio is a positive 4. We are multiplying by 4. Then after 20, my next term would be positive 80. And then after 80, I would have 320, and so on, giving me the geometric sequence. So here's a quick little introduction that we'll walk through. Example 831, a recent college grad finds a position as a sales manager earning an annual salary of $26,000. He's promised a 2% cost of living increase each year. Determine his salary for each year of the first 5 years he works at his job. So the first year he is earning $26,000. Then the next year he gets a 2% increase, which means we're going to be multiplying by 1.02 or 102%. We have 100% of what we earned before plus an additional 2%. So here I'm going to be multiplying by 1.02. And in doing so, I find that his salary is going to be $26,520. Then the following year we earn another 2%, so I multiply by 1.02 again, and in that third year we're now making $27,050, and here we've got some change, 40 cents. In the fourth year we get another 2% raise, so we multiply by 1.02 again for a total of $27,051.42, and in the fifth year we get another 2% raise, giving us a total salary of $27,592 and approximately 45 cents. So to get from one term to the next in this sequence, we multiply by 1.02. So here our A1, our initial value is 26,000, and what we call R, our common ratio, is 1.02. So a geometric sequence is a sequence that has a property that the ratio between any consecutive terms is a constant. This is called the common ratio R. And we're going to determine if each of the following are geometric. So going from 1 to 2, if I can multiply by a number consistently, then this will be geometric. So 1 times a value is going to give me 2, and that's going to be positive 2. Now if this is geometric, then I will be multiplying by 2 to go from each term to the next in the sequence. So 2 times 2 is 4, so far so good. Times 2 is 8, times 2 is 16. So it looks like we are multiplying by 2 between consecutive terms in this sequence, making it geometric with a common ratio of positive 2. Now for 48, I need to multiply if this is going to be geometric, so I'm going to multiply to get to 12, and I would be multiplying by 1 over 4. Well, 12 multiplied by 1 over 4 is not going to be 4. 12 multiplied by 1/4 would actually be a positive 3. So in this case, we have a sequence that is not geometric. They don't ask us to find the pattern for anything that's not geometric, so we're just going to go ahead and say it's not geometric and stop there. So to list out some terms in a geometric sequence, I'm going to start off with the first one, and then I'm going to ask you to do the second one. My first term in this geometric series, A1, is equal to 5. We are asked to write the first 4 terms, so A2, A3, and A4, given that my common ratio is negative 2. So all I'm going to do is multiply by negative 2 to get to the next term, so that would give me negative 10. I multiply by negative 2 again to get to the third term, which is positive 20. And by negative 2 again to get to negative 40 for my fourth term. Go ahead and pause the video and try out example 834 on your own. So here we're told the value of A1 is going to be 3. We're not told A2 or A3, but we are told that A4 is 24. So I multiply by a certain number to get to A2, and then by that common ratio again to get to A3, and then by that common ratio a third time to get to 24. What we are asked to find here is the value of A2. So what I know is that I started at 3 and I multiplied by r, then by r, then by r a third time to get to 24. So I can write the equation 3 times r to the third power is going to equal 24. And this is an equation that we can solve. I'll start by dividing by 3. So r to the third power is 8, meaning that r is going to be 2. So my common ratio is going to be 2. So 3 multiplied by 2 is 6, times 2 is 12, times 2 is 24. So sure enough, that common ratio makes sense, and A2 would have to be 6. All right, go ahead and pause the video again and try these next couple on your own. In example 345, what we're going to be doing is generating a formula for a geometric sequence. So given our first term is A1, we're going to write out the first 4 terms of our sequence. A1 is my first term, my common ratio is r, so then my second term is going to be A1 multiplied by r. My third term is A1 multiplied by r multiplied by another r, so r squared. To get to the fourth term, I take that third term and multiply by r again, so A1 times r cubed. To get to the next term, I take that previous term, which has r to the third power, and multiply it by another r, and so on. So all we are doing is increasing our exponents on r by 1. Notice that A1 has r to the 0, A2 has r to the first power, A3 has r to the second power, and so on. So if this is an n of 1, the first term in line in our sequence, the exponent on r is 1 less than that n value. If n is 2, the exponent on r is 1 less than that place value. For the third term in line, my exponent on r is 1 less, and so on for every term in my sequence. So we can use this pattern to help us write a formula for the nth term, meaning any term beyond A1. So A1, or A sub n, is going to equal A1, that first term, multiplied by r to the power that is 1 less than the n that we're looking at. So if I'm looking at n is 7, then I want r being to the 6th power. So I subtract 1 from my n value. And this will give us our rule for any nth term in a geometric sequence. And here is our formula just as we derived it for you as well. So go ahead and pause the video and try out now example 836 on your own. Here we're just writing a formula a sub n, so we want the general term for the nth term in this geometric sequence. My A1 is going to be 5, my r is a -2, and my power is going to be n minus 1. So if I wanted to find maybe the 15th term, all I would do is I would put in a 15 for n and simplify. They don't ask us to do anything with this though, they just ask us to write the rule, so here we are done. All right, go ahead and take a moment, pause the video again, and try example 837 on your own. We're told that each of these is geometric, so I'm going to write the explicit formula. So a sub n is equal to the first term multiplied by r to the power of n minus 1. So a sub n is equal to, here my a1 is 2, and it looks like my r is going to be positive 5. So my rule is 2 times 5 to the power of n minus 1. Now this is finite because our final term here is 6,250, and we are asked to find the number of terms n. So if this is a sub n, what I want to know is what is n. So what I'm going to do is take that a sub n and replace it for a sub n in my explicit formula, and then just solve for n. So I can do this by dividing by 2. I get 3,125 is equal to 5 to the power of n minus 1. And now to solve for that exponent, I can go ahead and use log. So log base 5 of 3,125 is going to equal n minus 1. To use our calculator, we can use change of base. Log of 3125 over log base 5 is equal to n minus 1. And using my calculator, I find that on this left-hand side, this is going to simplify down to 5 is equal to n minus 1, which means that n is 6. So that tells me that there are 6 terms in our sequence. For B, my a sub n is a 1, which is -1, and then we are multiplying by a -3 for my common ratio to the power of n minus 1. A sub n is 2,187. So I'm going to replace that for a sub n and then solve for my n. Dividing by -1, I have -2187 is equal to -3 to the power of n minus 1. And I'm actually going to use a slightly different approach here than what I did before. I'm going to write 2,187 as a power of -3, so that my bases on the left and the right-hand side are going to match. So -3 to the power of 7 is going to be that -2,187. Now that my bases are equal, I know my exponents must be equal. So n is going to be 8, which means that there are 8 terms in my sequence. Or in other words, we found that this final term, 2,187, has a place value of 8. So this is a sub 8, meaning that that final term occupies the 8th position. So there are only 8 terms in our sequence. And that brings us to the end of our discussion on geometric sequences for today. Thanks so much for watching, and have a great rest of your day.